Good morning, everyone. Welcome back to the Xendee University. I apologize for being 5 minutes late. We had some technical issues the first time here. We have now the DOD session where we talk about micro design and control in the government sector. We have three speakers here. Melanie Johnson from the Department of Defense, from the Army. Craig Vallery, he's a former Brigade senior engineer, also with the U.S. Army. And we have Jim Reilly here, working with the Department of Energy, and he will talk about micro-standardization work. I will flip a little bit the order here and start with Craig Vallery. Craig Vallery, as already said, is a senior Brigade engineer with more than 30 years of experience in federal services, supporting the U.S. Army, installations across the United States and especially in Europe. He has extensive experience leading large-scale facilities, infrastructures, modernization, military constructions, MILCON, energy resilience and sustainability projects. Throughout his senior roles, including facility engineer, Deputy Director of Public Works, Director of Public Works, and Chief of Engineer, he has overseen multi-million-dollar budgets, major infrastructure upgrades, and installation-wide operations. So welcome here, Greg, and the floor is yours, and I'm very interested to see what you're going to talk about here.
Michael, thank you very much. Here's the quick agenda, and I'm going to talk about what we call R2M2 architecture of electrical infrastructure projects. I'll tell you a little bit about my experiences in Italy, California, Germany, and back to Italy again. I'll talk a little bit about the overall processes that we've used where we've installed microgrids, and maybe a little lessons learned in the future of microgrids. So R2M2, what is it? We call it resilient, replicable, modular microgrids. We kind of coined that phrase or that acronym out in California, but I really took it as what I had witnessed and seen at various installations here in Europe. And really, it's consisting of substations that are very standardized. And typically the installations will have medium voltage cabling that ring all of these substations together. And then all the loads, the low voltage loads, are fed off each one of these substations. To complete the microgrid, you're obviously going to need the communications aspect of it and a control system. Okay. Now, some of these costs, you may find them unrealistic. But I'm going to tell you that these costs are very realistic here in Europe. So what does each one of the substations consist of? Usually these are precast concrete prefab boxes. They're very standardized. Inside them we'll have the medium voltage motorized switchgear, transformer, all the low voltage, and then the communication aspects of these. So what it ends up doing is making a very agnostic system where you can plug and play with a variety of power pieces, if you want to call them that. We could have combined heat and power. It could become a central energy plant, but it could also be distributed energy loads, et cetera, around the buildings or at each one of these substations. Ultimately, what we see is that the ringed medium voltage provides us redundancy so that if any one of the legs it goes down, then the power can be fed from the other direction. And each one of these nodes, we typically, if there are critical loads, we can make them operate as a low voltage microgrid as well. So I came to Italy first in 2002. What I saw was basically the R2M2 concept, very standardized. And I'm going to talk about 3 of the installations. during my first tour between 2002 and 2014. So Caserma Ederle is the primary base for USAG Italy. The initial idea of making a microgrid was when we combined heat and power into an existing older central heating plant. In the end, we used an ESPC. We put in two 1.5 megawatt diesel engines. The total load on the installation is around 7 megawatts. And so I kind of like to call this the hammer approach. The engines were big enough to support all of the critical loads, but they could not meet the peak load, obviously, if we only have 3 megawatts of electricity. Ultimately, what ended up happening, we did the ESPC portion, but then we came back and did the actual control portion that enabled those engines to become power for the microgrid. So later on, we added an additional 1.5 megawatts of rooftop PV and integrated. Over the years, things have improved, et cetera. But this was the first experience really for the installation. The second installation I'll talk about was Del Den. That was built about 12 years ago. It's been in operation during that time, and it actually ran for the first year and a half on the CHP project, the CHP that was there on the site. This was a major Milcon project. The whole installation was built out as new, and the central energy plant was part of that overall design project. It was executed by the Navy. And I think it's approximately 2.5 million square feet in total. They've subsequently added the rooftop PV, approximately 3.7 megawatts. They've done further ERSA projects where they added chilled water, hot water storage. So all the district heating and cooling comes from the CHP plant. So if you were thinking about how to do a plant from start to finish, an entire installation, this one went through that entire process. Another installation is down in Livorno. It was underneath USAG Italy. Again, all of these projects ended up using the R2M2 concept because it was already laid out like that. Difference down in Livorno was they did not have a district heating facility already established. And so what that facility will ultimately look like is more distributed PV. There are already 7 large systems on warehouses that have 1.4 megawatts. But again, a little bit different ways to handle things. One thing about back at Del Den, I call this one the sledgehammer because the engines were more than sufficient to run the entire facility. No load shedding is required, but certainly provides added flexibility and capability. So after my tour in Italy, I went to California. That's also where I met Michael Stadler early on when he was back at the Lawrence Berkeley National Lab. Both of the installations in California that we were responsible for, Fort Hunter Liggett and Camp Parks Reserve Forces Training Area, were the Army's net zero energy demonstration sites. This was the first time that we actually used Xendee to start looking at loads and how to set up and operate these installations. Ultimately, Fort Hunter Liggett has completed their microgrid. It came online about a year ago. I will say that it integrated a lot of various parts and pieces. There was 3 megawatts of PV that were originally there that were installed between 2012 and 2016. But the overall microgrid, which included battery, a large battery system, et cetera, as well as additional PV, all came to fruition during the past 5 or 6 years, really. When I was there, we also did a design and started a process to do a distributed Camp Parks version. And I will say there is a large difference between Fort Hunter Liggett and Camp Parks. Fort Hunter Liggett ended up doing a sectionalized microgrid versus the each one of the distributed nodes, substations, if you will. So we'll get a little bit more details on those. Next up was I moved over to Germany, and initially that was at Garmisch. Older installation. It was fed off of a district heating system from a CHP that was operated by the city. There was 4 low voltage distribution systems that we modeled under Xendee and looked at those for optimization and backup power, et cetera. Our critical loads, by and large, already had generators that were there as their backup power. But what we were looking at was how to do the optimization of each one of those points of delivery. And we put together a package that included PV, rooftop PV, battery storage, and the existing generators to work together. Another project that I worked on while I was in Germany was at USAG Bavaria, Grafenwehr, and Hohenfels, and we're going to dive a little bit deeper. What we did was a very extensive modeling and assessment. And what it was related to, and maybe most people not familiar with this, these installations, but Grafenwehr and Hohenfels are large training facilities. And one of the major Milcon projects that was basically already planned, but we started the initial phases of the projects is an operational readiness training center or complex. And what it was looking at is a variety of assets, all these building assets that is everything that a unit needs to fall into and basically be on site doing various training for an extended period of time. And you can see from this and the number of buildings, these are not small items. This is over $1 billion of military construction. And we went through a series of modeling and assessment to determine what is the best way to operate these facilities. Okay. So we ended up doing four scenarios on how to operate these. I'll say COA 1 is probably the kind of gives everything in a central plant and then distributes everything, hot water, chilled water, all the power is coming from a CHP, et cetera. There was a COA 2 that basically adjusted that slightly. COA 3 was where we looked at a kind of a distributed scenario. All right. And this was basically with ground source heat pump. And so there wasn't the backup power plant was pretty small, but it was there that supplemented the PV and the battery storage that were in place. And then another version was also to integrate some heat recovery off the combined heat and power plant, et cetera. So we didn't have to rely quite as much on the number of geothermal bores, et cetera, for all the heating and cooling. So ultimately, every one of these buildings were modeled and trained trace on a hourly ASHRAE compliant model. So we had each one of the facility types. There was 9 facility types, and basically looked at their load profiles. And sorry about that. And so we ended up looking at each one of these options, these COAs, after they were modeled. We determined all the sizing requirements, et cetera. And then we did the net present value. And ultimately, what you're going to see here is that COA 3 was the cheapest of these 4 options. Okay. But then again, it not only was the cheapest, it also was the lowest energy consumption for the size of the facilities. And effectively, we were able to pretty much come close to cutting all the energy usage in half. I don't think anybody really anticipated it. Everybody thought that the providing cooling in these facilities was going to make all these options really expensive and energy intensive. But here you can see that actually in 2019, the overall energy usage for USAC Bavaria was 205 kilowatt hours per square meter per year. These facilities, as modeled, were basically going to cut the power requirements in half.
Greg, just for clarifications, also for the audience here, what was the reason that you wanted to electrify the whole system? I mean, I remember something vaguely here, but there was something regarding that you want to get completely off natural gas. Is this correct?
Yeah, that is correct, Michael. Of course, Germany has been historically highly reliant on Russian natural gas. Obviously, for us, that natural gas could be at risk to be turned off. I think we've seen a lot of different things happen since 2020. As these things have gone through, I think we all see the risk, at least for Europe anyway. Italy's not that much different. Heavily reliant on outside sources for fossil fuels. As we ran through all these numbers, though, what we also found out was over 80% of the all-electric solution could be provided just by putting PV panels on the roof of the facilities. We also considered that the ORTC is a mission-critical asset in and of itself, right? It's not like we have the ability to stop training soldiers if there's a requirement for them to be ready to be deployed. The other thing I'll bring up is that, a lot of times we say, well, this is not a barracks may not be a critical facility, but it can be in these training environments when the soldiers basically have to live, eat, and train all in those facilities. And so the other thing that's kind of good about running all the modeling was basically coming up with the thought, hey, not only do I know the amount of energy that's required, the peak power that's required, but I also know when it's required. And obviously, Xendee helped us go through the process and model the appropriate size of all the PV, the energy storage, et cetera, and how it all came together. Those net present values were based upon the amount of those assets that were also being installed. Okay, I'm going to go a little bit more in depth in a very recent project. And I worked this project over the last 5 years. We started by using Xendee to model a small installation, and this installation is home to the 207th Military Intelligence Brigade. Our facilities are all critical facilities because these are where these soldiers work out of. The facility already had kind of the same R2M2 electrical system architecture. It was all a little bit antiquated, but we ran through the modeling. We looked at the existing generators that we already had, and each one of the 5 substations already had an existing generator. And we looked at how best to augment that with PV and battery energy storage. This is just a general layout of the facility. The items in green are the medium voltage electrical substations. They are in a ringed architecture that kind of runs around the perimeter of this installation. And each one of these are all connected and can operate together as a microgrid, or each one of them could be separated to be a low voltage microgrid. So I'm going to tell you about our process, right? So I already knew a lot about the facility before I came here, but when I got here 5 years ago, we basically went into a process. We looked at all the loads. We used Xendee to come back in and identify the loads, the load profiles, and to help us model the right size for the assets. But I'm going to talk through each one of these very quickly. You need to measure, and of course, the better the data is, the better everything else is better as well. So model, design, get it under contract, construct and install, control, commission, and operations and maintenance. This was our load profile. The peak demand was just a little bit below 250 kilowatts. Total energy use for the year, you can see it on the slide. I think our average load is about between 100 and 110 kilowatts. So that kind of gives you just a general idea. It's not a huge energy load if you want to think as far as normal installations go, because it is relatively small. We have approximately 80,000 square feet of facilities on site here. Everybody remember what happened here in 2021? What we saw was that energy prices in Europe, because of the Ukrainian-Russian conflict war was going on, had a dramatic impact on energy prices. And so you can just kind of see these. And effectively, we're talking about going up from 10 cents a kilowatt hour to almost, in some cases, 50 cents a kilowatt hour. So modeling, I won't go into great detail here, but you got to go through the modeling to determine what you need and then how best to configure it and lay it out. We looked at all the various distributed energy resources. We ultimately, after the model, we developed a design. During that design, they also ran ETAP, okay? And we did this all through a Xendee GSA contract. And we did it through the Corps, who then went to the GSA to assist us with the modeling and design. And here's some of the scenarios that we ran in the modeling scenarios, okay? The summer and winter, the variance there, we looked at it based upon the kind of a worst case for some of these things, specifically with the PV and some of the facilities. Most of these facilities either already have been converted over to heat pump, but we've gotten rid of the boilers. They all had boilers with fuel oil tanks, but these were all either changed over to heat pumps or have designs and projects ready to execute to continue to do that. The outputs here from Xendee. Ultimately, if you look over at scenario 4 in the winter, we ended up choosing that for the solar, 1.4 megawatts of PV. And the battery storage size, we chose the summer scenario for scenario 4. So 1.8 megawatt hours of storage. We'll probably end up with more than that. We're going to put about a 500 kilowatt hour BESS at each one of the individual substations.
Greg, can you go back, because this reminds me of something, and if I have this in mind correctly, might be interesting for the audience. As you see, we have this OpEx here, right? And Greg, I think if you remember correctly, it was actually not the net present value or the capital cost that were mostly interesting for you guys. It was really the OpEx savings, right? Do I remember this correctly?
Mm-hmm. Right. Yeah. And that's really, I think, something that it's not only your energy savings, but there's operational savings associated with some of these scenarios. When like we had talked about the Hohenfels and Grafenwehr project, the ORTC project, we're talking large cost numbers there. But when you run the net present value, obviously over time, that really does start to add up. So when those savings are realized. So.
Yeah.
So, this just kind of relays it all back. Everybody wants to do the right thing. You got to spend a little bit of money to do the right thing, but not as much as you may think. I don't want to put Michael and Xendee on the spot here, but they really helped us out. Huntsville, I think we paid them $75,000 to be awarded the small contract that provided us the analysis and design for our microgrid project. And that included not only just the microgrid piece, but also the distributed energy resources that we ended up putting in together projects. So we're doing this little piece at a time, but overall, all the projects have been designed and packaged so they are executable as funding becomes available. We actually installed the microgrid piece, which included various medium voltage breaker upgrades, communications, all the pieces that make this pull together and be able to be operated. Integrating the existing diesel gensets, et cetera, was slightly over $700,000. And we did it through what's called the job order contract. Okay. So real quickly, I'm going to hit back on some of these things. So we got the design piece. Xendee is excellent for providing all those upfront sizing and analysis. I would also say we've used ETAP successfully. And in Europe, there's a software system called Integra Excel. It includes all of the major manufacturer components in there in a library. So when they go through the design, they then model it in here, and then they pull in all the elements that are needed, and they automatically get a list of materials, whether it's from Siemens, Schneider, or ABB, but basically they already know what they need to build it out. Okay. So construction, obviously, a key piece of it. What contracts are out there and open for the installations to use. Again, we've done some of all. Delden was done by NavFact under a large Milcon project. However, other ones, just like the one we're talking about now at Vallery, was done, I'll call it, with probably the simplest and easiest to use tool, the job order contract. So we've also done with the ESPC and the UESCs as well, at least portions of the microgrid projects. Controls, a critical piece here. Obviously, you need a standalone isolated network. You don't want this thing having too many vulnerabilities. You have RMF certification. All the facilities that were built have a control system that has gone through the RMF process. I can tell you that they use ABB predominantly here in Vicenza. The ones down in Livorno were using Siemens. So again, they make a lot of the components associated with it. Both of them do. But they also make their own control systems, and they have successfully gone through the RMF certification and authority to operate. Operational scenarios are critical. A lot of people may not fully grasp that sometimes it's not when you're operating in a steady state, et cetera. It's when you switch from all these phases to include a black start that everybody has to plan for to make sure that you can restart it if things are not already online or they have to go offline. So commissioning, right? You got to test every one of these scenarios and go through all the cycles. And I will also say that you probably need to do exercises frequently on the system to ensure things still operate correctly. And for sure, like most things, building a team is very difficult. Getting all the right players on the team is difficult. And getting a common goal and the right concept of how things to get done requires that competent team and to come together. And lastly, it's not only after you build it, somebody's got to operate it and maintain it. We're fortunate in Italy that because they already had central plants, they had competent operators, they had personnel that were going to be on site 24/7. They have training for the electricians. These guys can switch out transformers. They know all about the control system. They know how to do the diagnosis, and they know how to fix stuff when it breaks or when something goes offline. That concludes the brief.
Thank you, Craig. So there are a couple of questions from the audience and also from me, and I apologize that we're running a little bit late, but I want to have a couple of questions, and after this session we have a little bit of time as a buffer here. I also apologize for Greg's camera because somehow government workers and DoD is not really happy about Zoom. So there's some challenges when it comes to DoD accounts, and this is why you don't see probably Greg's camera here. But Greg, there's a question. For new projects, is the Department of Defense exempt from FEOC? I don't know what it means, FEOC.
I don't know either, Michael. So
FEOC. So maybe Vince, maybe you want to spell it out. Maybe I'm just saying it wrong. Greg, you see the question also in the Q&A section. If you go down, maybe it means then something for you.
Okay. Hang on here.
Oh, okay. Foreign entity of concern. Okay. So basically parts from other country. Greg?
Yeah. Can you hear me?
So the definition for FEOC is foreign entity of concern. So did you have any issue with that?
I'm not even sure what that is. So
Okay.
I'm sorry.
Okay. Oh, I think Melanie has.
I guess I can answer
Yeah.
that. We must not had that concern.
So I think if we're asking about like supply chain, can we buy things from foreign entities of concern? For example, like energy storage from, a lot of the manufacturers are Chinese. The answer is no, we cannot. We have to follow the Buy American Act, which insists that we purchase primarily American-made or American component technologies. So I think that's what that question's asking about.
Okay.
So, but how does this play back to Siemens and ABB then in Italy?
So, well, Michael, I can tell you that the most of their switchgear is still manufactured here in Europe. So I don't think for those items it's an issue. I'm sure for the batteries that the actual cells that are inside some of these battery systems are certainly made in China, right? I don't think, unless we were buying Tesla, we're going to probably, or something out of Korea, we're probably not going to be able to avoid a lot of that because the cells are still, predominantly manufactured there. I think we kind of get around it a little bit because we're buying it from an assembler who is not in China. Certainly here in Italy, I've toured one of the facilities that does the assembly of the cells, et cetera. So it was a local factory that does it. So.
Okay, I think we keep some of these questions for later on, also when we have heard Melanie. I have one last question for you, Greg, and I'm asking this because we have worked together for a while, and I was always wondering, I mean, what your biggest challenge was to get these projects through. So maybe you have a point about this, because they were really lengthy and complicated. So what, in your perspective, what's the, I mean, and I guess it's not the modeling, there's something else which probably has to be overcome to power through this long project. So what's your advice on this?
Yeah, so you're right. Getting anything through the government wickets is challenging. Getting it through like it needs to be done is even harder. I think that was one of the benefits associated when we were able to get something like the evaluations done up front and enough of the design completed so that the project could be adequately presented and the benefits could then be shown. And once the benefits are shown and they can be quantified, then somebody is much more likely to fund those projects when they're planned. Mm-hmm. And it looks like they've been well developed and thought through, et cetera. So then it becomes executable. And that's really getting a project that's ready to award, that is a good project, that obviously presents well, has good benefits, et cetera. Those are key, to putting your project at the top of the list. Yes, because somebody's going to see it and they say, I want to fund it. So, and be ready. Okay. Obviously, they can send you money, but if you're not ready to execute it, you can't do it.
Okay. Thank you, Greg. Okay. Thank you. So let's switch over now to Melanie. Melanie Johnson is an electrical researcher at the Energy Branch of the U.S. Army Energy Research and Development Center's Construction Engineering Research Laboratory, ERDC CERL. That's a long name. Melanie joined the Energy Branch at ERDC CERL in 2008 and focuses on improving energy resiliency for the Department of Defense installations with microgrids and other advanced electrical distribution technology. This work includes incorporating the diverse distributed generation portfolios into microgrids and microgrid project lifecycle planning. She was the Assistant Technical Manager for the JCTD SPIDERS program, a key technical lead for the Tactical Microgrid Standards Consortium, and currently leads CERL's Resilient Energy and Advanced Distribution Innovation Team. So with this, I'm handing it over to Melanie, and very interested to hear what you have to say here. Thank you.
Awesome. Good morning, or I guess now it's still morning here for me. I'm really excited to be here with you guys this morning. Michael, thanks for having me here at Xendee University. So I am going to share with you guys how we are planning and executing microgrid projects that are coming through our Energy Resilience and Conservation Investment Program, which is our large military construction program that's funding most of our microgrid development at our installations. So the motivation for the Department of War to build microgrids on our bases really comes from a few places, but we get our official definition and our kind of legal definition from the FY22 National Defense Authorization Act, which basically is the same definition you'll see everything else. It's that integrated energy system of multiple loads and multiple energy resources that can island from the utility. The other driving factor that we have in planning our microgrids is Army Directive 2020-03, which tells our Army installations that they need to plan to sustain their critical missions with energy and water for a minimum of 14 days. Now, there's some flexibility that's come about in that requirement because a 14-day requirement for everything is pretty intense. So at this point, our mission owners, our mission commanders, our garrison commanders are allowed to say, look, it doesn't actually need 14 days of resilience. We could get by with 10 or 7 or 5. They're allowed to walk that requirement back, but that's the kind of design basis that we use for planning our microgrids. And the goal when we're thinking about microgrids for Department of War installations is to get to this energy resilience via defense in depth, right? We want to use commercial utility power because that is the cheapest, most efficient thing for us to do in most cases. And that's our normal operating condition. But we want to create these fallback positions within our distribution systems where we can have large on-site generation that provides most of the load at the base, that we can use either to offset our energy costs or to island from the grid. or to create better stability within our grid regions. But if that is unavailable, for example, if our distribution system is damaged, a lot of these larger generation resources rely on natural gas, which is of course dependent upon our regional electricity systems. We have these other fallback positions within the base where we can fall back to networked generation that's co-located at our most critical loads, so that those most critical loads can stay on the longest with a increasingly degraded system. So that's really kind of the design objective. Now, this is not where we are today. This is the goal. This is where we're trying to get to as we develop more microgrids at our installations. As the year, we started with a few, we have a lot more. But again, this is the goal. This is not where we are today. Okay, so right now, this 28 number is probably a little bit dated. We're probably up in the 30s at this point, but we have around 30 operational microgrids at 22 different installations, but we have over 70 microgrid projects in various stages of development, from conceptual design and idea generation to things that are in an A&E design process to get to 100% constructible design. And we have lots that are currently under construction and a few that are entering commissioning and operation. So how are we getting there? So the Army Corps of Engineers, which the lab that I work for is part of the Army Corps of Engineers, is responsible and manages microgrid design and construction for all ERDC-funded Army microgrids. So in FY22, the Corps of Engineers made the decision to consolidate our ERDC execution into just a few parts of the Corps of Engineers. Prior to that, when an installation would get an ERDC project to build a microgrid, it would go to the geographic district associated with that installation. But what we were finding is that our districts weren't really prepared to manage microgrid projects and didn't have the contractors available, or didn't know how to get to the right kind of contractors to get a viable microgrid design. And so this decision to consolidate the ERDC program into just a couple of places was to get better execution and to build some expertise that would actually get good results out of these projects. So this is how it stands after FY22. So when we talk about developing microgrid ideas, right, our installations will generally do the first draft of that design. They might work with another office, like the Office of Energy Initiatives. They might work with a DoD, FFRDC. They may even work with a contractor to come up with their initial microgrid concept. My team at CERL also offers microgrid conceptual design directly to installations. So from those efforts, we generally come up with a draft 1391. A 1391 is the document that Congress approves for a military construction program. So it kind of outlines scope and cost and gives an idea of what that project is supposed to be and the purpose that it serves. So at this point, we have a draft, and there's a packet of information that the installations submit to apply for an ERDC project. The ones that are going to move forward in this process, so they're down selected at higher levels, they come back to us at the Corps of Engineers, where we do 1391 validation. So this is primarily a Corps of Engineers Huntsville responsibility. So they look at those 1391s and decide and validate that design. They go and check with all the engineering disciplines that we don't see any obvious showstoppers. They look at the cost estimate and make sure that's feasible, and perform this process for all of those potential projects in 1391s. Those go up to a selection committee at the Office of the Secretary of War level for the ERDC program, and some of them come back selected for project funding. That's when we get the planning and design funds that allow us to do 100% design, and those are run out of Huntsville as well. And then we move to construction at Corps of Engineers Louisville District in conjunction with the geographic district that the installation works with. And then we get to the end of the project where we do testing, commissioning, and sustainment. So we were implementing this process in FY22 and realizing that we had a really wide spread of quality between the DD 1391s that we were seeing come out of this process and enter validation. We would have ones that were really excellent. Greg gave you some great examples and case studies of projects that received a lot of attention and got a lot of had a really knowledgeable installation staff that was able to develop the 1391s. Or Greg, you may have gone after the funding methods, but at some installations we get really, really high quality stuff, and at some installations they don't have the manpower, they don't have the staff, and so they're putting a project forward, but they just don't have the capability in house to provide something that's going to be sufficient to get an ERSIP project. Sorry, I'm actually going to.
Since we adopted an approach today where I'm interrupting people anyway, can you go back to slide 5? I have a question on this.
Sure.
Does this actually mean that for the detailed design, you're not going with external companies anymore, or is this?
Oh, we absolutely are. Sorry. Yeah. So the A&E design in Huntsville, there is those are typically A&E design engineering firms that they contract with to do those 100% designs.
Okay.
So
it's
absolutely. There is a contractor that comes in here at the A&E design step. And the reason that we're able to go to a contractor at that point is because we have planning and design funds associated with the military construction project.
Right. Mm-hmm. Yeah.
So I'll talk a little bit about why the funding is complicated in early stages in a second. I'm gonna come back to that really complicated slide. So starting in FY25, after we were looking at these 1391s and going, wow, we really need to support our installations better, and coming up with high quality draft 1391s that are competitive for ERSIP projects, that's where my team comes in at this point. So we came up with this, we call it the advanced planning process. So this is before we have planning and design funds, before these are recognized military construction projects. We come in and we do some basic data collection with the installation. We review that data and look through where are the data gaps? Where are we seeing maybe potential problems with what they've come up with, or they may not have anything at all, and we're doing this from scratch with them. We look at if they have an electrical one line, we look at that. We try to come up with some estimate of load data, or if they have interval load data, that's fantastic. So we kind of work with them to get the best data that we possibly can. We do a design analysis where we come up with a potential microgrid based on their needs and their critical mission loads and what resources they have available, and talk through that with them and make sure that they think that's going to meet their needs. And we document all of that as a draft conceptual design or an advanced planning report that can now be linked to that 1391 and go with it into the future. And the idea is here that we get a more consistent 1391 going into competition for ERSIP funds. We have a much higher confidence level that these are viable microgrid projects, that we have caught some of the big showstoppers we've seen in the past, like, oh, it would be great if we built a CHP plant, but actually there's no natural gas line large enough at this installation to support that. Or it would be great to build this microgrid, but it doesn't meet our microgrid design criteria that the Corps of Engineers has in UFC 3550-4 or 04. So anyway, there's a lot of little details that we can catch really early that makes it a better product for ERSIP competition, and then a much easier thing for our design teams to pick up and do their 100% design. So all of that fits into this much, much bigger, more complicated picture. I don't want to go into detail, but I thought this, how complicated is this government acquisition beast? It's very complicated. My team fits over here in these early requirements and scope generation. What we just talked about, Michael, that contractor design team does the 100% constructible design. And then that's going to get handed off to a construction contractor these days, but to work with Louisville to do that construction on the base. So, okay. So what do we put in these advanced planning reports? I'm sorry, this slide apparently has some timing that I didn't realize was still there. So our main goal with our advanced planning reports is to provide a geographical footprint for the microgrid, a simplified, approachable electrical block diagram that helps folks that are not electrical engineers understand the structure of the microgrid and how it will function. We do some generation portfolio sufficiency analysis. We call it load analysis, and it's one of the places we've been looking at commercial tools to expand our capability, improve the quality of this analysis. And we provide a ConOps, a concept of operation. How does this particular microgrid intended to function? How does it move between its different modes of operation? So some constraints that we have on this process. We have to move really, really fast. We get about 6 months each year to come up with these advanced planning reports and do this conceptual design work. Like I just mentioned, these are not real recognized projects yet, right? They're headed into the queue for competition with other projects from other services, with each other. And so because they're not recognized, they don't have planning and design funds attached. They don't have actually MILCON project numbers yet. They're in early advanced planning. And so we don't have budget beyond like our operation maintenance funding or SRM funding to support this. So our budget is very, very tiny. And that's been one of the reasons that we haven't looked at using contractors for this work. It generally, my team working very fast is less expensive than trying to go to a contracting model. We're also doing multiple locations. So we, on the lightest year we've ever had was about 5 installations since we started doing this. And it goes all the way up to about 15 installations per year that we're trying to do this in 6 months. The other thing is that data is very scarce. We try to request the bare minimum that we need to be effective from our installations, and we often are not able to get even that request. So what is that request? This is generally the list of things we ask for from an installation. That installation electrical one-line diagram is occasionally very difficult to get a hold of. Many of our installations have privatized utility contractors. That means that we've sold basically the electrical distribution system to a private party, and they own and operate it on our behalf. And depending on when that contract was awarded, what's in it, they may or may not be obligated to share a one-line diagram with us. We also have some issues with privatized utility contractors and it requiring some sole source contracting, and we have to get very special permission to do that. And in some cases, we did get the special permission, which was in the form of an actual act of Congress. They put very specific language into a National Defense Authorization Act for us, and it still wasn't quite enough to make that sole source happen efficiently. There's still some things that had to be worked out about it. So we have some issues there getting one lines. Sometimes we can get a distribution map if we can't get a one line, and we work from that instead. The other thing that we generally have a really hard time getting a hold of is installation electrical demand data. So we have a mandate in the Army that all of our buildings be metered. Right now, only about 11% of Army buildings have electric metering on each facility. Often the best we can do is whole installation demand data, right? Like at the main meter, which if we are talking about a big base like Fort Bliss, the peak load in the summertime is like 100 megawatts. And if we're trying to do some small subset of the base, it's really hard to tease out what we are actually trying to microgrid from that really big bulk signal. So demand data remains a big challenge. So that's kind of when we talk about data scarcity in this process, those are the main ones that we're talking about. But they're very important to developing microgrid conceptual designs. So we do our best to work around it. So sometimes when we are doing like this load analysis, depending on what we have from the installation, we might be able to do a really nice, interval by interval analysis of how the generation portfolio will meet the needs. We may be able to do a great model in commercial software. And sometimes I have 2 numbers. Sometimes I know the peak load and the average load. I have one I'm working on right now where I don't even know the average load. They only kept track of their peak. So it ends up being sometimes, unfortunately, just back of the envelope style math to come up with like, well, if this is your peak, then the worst case scenario is that you use this many megawatt hours a day. And we go from there. So we're really working sometimes with very limited information. Okay. So the other thing we did a couple of years ago was start to look at what kind of studies do we need to do and where in the process? Like, when can we afford to do these studies, and when do we have the data and sometimes people available to do them? So we're trying to take this position that we can't really design a microgrid if we don't have a one line. There are still some places where we are told, no, we still need a microgrid even though there's not a one line. But we're trying to say, you got to have that done before, like, do not apply until you have a one line you can hand us. That load analysis study where we're just looking at how generation portfolio meets the demand, that's where we've obviously moved that into our advanced planning list of activities. So that's the one that this talk is focused on the most. We have a few others. One line capacity analysis is just the idea that in that advanced planning, we don't have the time or often personnel funding to do a full load flow analysis, but a skilled engineer can look at a one line and say, hey, if your cable is only this size and you're planning to hook up a giant power plant to it, you will have to upgrade that feeder. And so that's what we're trying to catch early and when it's obvious with that study. And the other ones that you're probably more familiar with that are absolutely required, those we have to keep in that A&E 100% design process because of how intense they are and how much they cost, especially if you are starting very much from scratch. So just to kind of give you an idea of like, how are we organizing our studies? This was an effort that we did with Idaho National Lab a few years ago to figure out what needs to happen when. So we are looking for and trying to get our hands on software tools that help us overcome some of those constraints and lead to better designs early on so that those early 1391s are more representative of the project that we actually need to build and the cost associated with it. So in the past, we had a Searle-made load analysis tool that took installations data and matched it up with the generation portfolio on an interval by interval basis. And there are some really nice things about this old tool that we wrote a long time ago. It's really fast for us to implement. It doesn't take a whole bunch of people. It does require interval data, which is a drawback. It doesn't have any optimization built in. It's just run a few different studies, compare the results, and then if you have looked at enough of these, you start to get an idea of what the sweet spot starts to look like at the end of a load analysis. So it does take an engineering staff to interpret the results. The results of this are all focused on resilience, right? I'm not trying to show you the life cycle analysis. I'm not trying to tell you the return on investment. I'm just trying to see if I have any load not served and how much of the PV did I capture? Do I need a bigger energy storage unit or do I need a smaller PV array? But we also don't have to purchase it annually. We started looking into commercial tools and we've had some really good experiences with those commercial tools. Michael, I'll say the lawyers had a lot to say about what I am allowed and not allowed to say on this slide. So I will say the commercial tools that we've used are also very fast to implement. We love the data libraries that are built into those that give us ability to fill in some of those data gaps we have and use much better models than are available in our tool for a number of generation resources. The cost and resilience optimization available in the commercial tools is really a step up over our homebrew. And the automatic report generation provides these really nice polished products that we can include as appendices to our reports, which is great. And having the economic analysis is also really useful. One of our drawbacks and the situation that we're in right now is that the annual purchases have to go through our acquisition programs, which they just take a while. And that is always a recurring working for the government challenge. Is acquiring stuff often takes way longer than you would like it to. So let's see. So just thinking about how we move into the future with all of this, we know that the situation we're working in isn't going to stand still, and we design all of our microgrids right now around historical data. So we're always looking back at the past and we have some constraints about how much expansion or load growth factor we're allowed to include in our ERDC project requirements and specifications. So we know that demand is going to increase. We know that tactical loads tend to have really funky load profiles that may give us spiky demand profiles into the future. And there's a increasing emphasis on these really energy intensive tactical loads. We know that we have aging distribution systems, that we can exceed the limit of what those distribution systems are capable of carrying. And when we've used historical data to design the microgrid generation portfolio, we know that that generation portfolio may not meet their needs, even in the near-term future. So we are, we know all these challenges are out there, and that we need ways to account for them and mitigate their impact on the microgrids that we do build, especially ones we're building now. We'll need to mitigate these challenges in the near term. And so thinking about it in the context of tools that help us show what the impact would be even of minor load growth are ones that we're very interested in looking at in the future. And I think, yeah, that was my last slide. I'm happy to go back and talk about anything in there in more detail, answer questions, whatever.
Thank you, Melanie. There's one question, and then I think we let Jim talk, and then we can have a conversation at the end if more questions are popping up. But can you go back to slide 9? There's a question around slide 9, because it sounded like that you're doing these project analyses without actually knowing if they're getting funded, right? So you're doing this probably, and then you have to wait and see what's getting funded. So you're doing this basically for free and without knowing what's coming out of it. Is this correct?
I'll get the slide back up. So we don't do it for free. We definitely do get paid. It's just that we're not getting paid from like the funds that gets later get set aside for the project. So let me advance here to slide 9. Yeah. So right now, my team here at Searle, we work for the Office of Installation, Energy, and Environment. It's one of our Deputy Assistant Secretary of the Army offices. I don't actually know what pot of money they are using, but they are the ones that sponsor our work so that they get high quality competitive 1391s to feed up into the ERDC selection process.
Okay, so it's a service for the installations, and then later on it gets decided what really will be funded, and then they can go into the detailed design. Yes. Okay.
And we do occasionally work directly for the installations. We had a fantastic opportunity a few years ago to work with Wiesbaden in Germany. We did some preliminary work for Camp Humphreys. So we do occasionally work directly for the installations when they have funding to support this kind of effort.
Okay, thank you. There are other questions, and hopefully we can get to them after Jim's presentation. So thanks, Melanie, and I'm really thankful for your time here, because I know it's not easy to get approval for these talks, Melanie. So
it went surprisingly smoothly. I'm really happy that I got to join you guys today. Thanks.
Thank you. So can you please, so now Jim, Reilly, please start sharing your screen, and I'm getting to your intro here. So while Jim is trying to get up his presentation, Jim Reilly is an independent consultant focused on advanced microgrid concepts that support energy security, grid reliability, and resilience. Among his clients are the U.S. Department of Energy Microgrid Program in NATO. In Japan, he's the author of multiple reports, standards, and guides for microgrids and virtual power plants. He's a co-author of the Advanced Microgrid Report, developer of modeling and analysis tools for planning studies for distributed energy resources, including small modular reactors and for data centers. He's a lifetime member of IEEE PES and recipient of the IEEE SE Emerging Technology Award for 2024. So, Jim, thanks for your time, and I'm also looking forward to your presentation regarding standardization and control.
Well, here we go. Can you hear me, Michael?
You're coming through fine, but we don't see you. Maybe, Jay, we have to unlock his camera here, Jay. Otherwise, there's also a problem with the camera.
Well, I was disabled by your host, but I figure you've probably seen enough of me already.
Yeah, well,
oh, okay. I'm still disabled, but that's okay.
No, we see you. We see you. We see you, Jim. Go ahead. We see you.
You do? Okay. Michael, do I still have the 30 minutes? My presentation goes into the future, which is infinite, but I'm not going to talk that long.
No, you have 30 minutes.
Okay, thank you. I divided my presentation into 3 parts, and part 1 on the evolution of microgrids and controls actually begins with the Department of Energy working off of the Spiders program that Melanie mentioned. And I wish at the time that we'd known that earlier than that, Mr. Vallery had been able to, or we'd come to discover what he had done, because he'd been doing a lot of good work with CHP earlier, and we could have benefited from knowing him. But that's one of the problems between Department of Defense and Department of Energy microgrid program. We would like to actually share some of the advances that we've made through the standards activities and through the applications that have developed with Xendee, across the entire government. But it was really good to be tied with the beginnings of a lot of things, going back to 2000, 2012 in particular, when control issues through the start of the 2030.7 standard for this functional specification for microgrid controls was started in 2012. That was the incubation period. I've been working with data centers and with microgrids and microgrid control systems since the very beginning, and very soon after the beginning, discovered the power of the work that Michael was doing, first at Berkeley with Durkheim, and now with Xendee, which is progressed at geometric rates. So let me proceed to these 3 parts. It's part historical, but the history has really been quite predictive of interactive microgrids, interactive with the grid services. It's just that this didn't have a big demand. The demand in the past, up till very recently, is for resilience and backup power and that sort of thing, where the control systems now are being used at a much more elaborate, let's say, level. Okay, I've got to change this here. Is it not? There you go. So here we go, part 1. We have a defined boundary, which makes a microgrid rather than a VPP, which is an aggregation which goes across boundaries. We're talking here mostly about grid connected that then becomes islanded. And then we're advancing into intelligent controls, controls that are innovative, optimizing both from the design and from an operational standpoint. The definition that you see at the bottom there, a localized group of electricity sources and loads that normally operates connected to and synchronous with the traditional centralized grid, but can disconnect and function autonomously as physical or economic conditions dictate. So we're starting out with something that involves the grid and connects to the grid and interacts with the grid, even though it may island. Military bases often are only microgridding a very, very small portion of their load. And this needs to be interactive with what's happening with the grid and the supply from the grid, the reliability and quality of power, which is one of the things that I raised in a question to Melanie because of what's going on in Northern Virginia being crowded out. So there we go. That's the microgrid that we're talking about here. The evolution in each of these eras, we started out with simple island power. You had a generator. You usually had just droop control when you wanted to be sure that you were protected against something that was going to happen with the grid, or there was, God forbid, a blackout. Then you move to another period where the DOE actually started to do its research program in microgrids. This all sort of gestated, and it was propelled in a large part by the smart grid work, and NIST had a lot to do with it at the time. And also the Japanese NATO contributed many use cases, which are highly relevant today, all uploaded to the EPRI use case repository. And many very advanced things were developed then in terms of aggregations. For example, the aggregation of energy storage as a virtual power plant is one of those use cases developed way back then. So then we start with the standardization projects, which have been actively supported by the DOE and actively contributed to by our very own Michael Stadler. You'll see levels of control systems later, and they had their genesis in work that Michael was doing and thoughts that he had, insights. Now today, we are in the hyperscale area. Even though 10 years ago there were 100 megawatt data centers, the FDA in White, and just off the Beltway in Washington, there was 100 megawatts. But now we're having gigawatt level microgrids for data centers connected to the grid, autonomous, as bridges to when we will have grid power available from nuclear. And then, of course, there's all the integration of all the different technologies. And then, of course, we want to introduce, the value to the grid itself, because these large loads that are out there are kind of important to be dealt with. The standards process has anticipated this, written about it, and had the functional analysis in there. And then you'll see later that we're updating that process. Each era expanded the scale, intelligence, and grid interaction, which culminates in what we're working on today. This slide gives you a few details. I'm glad that we put into the details on the microgrid program of the DOE, because the DOE was supporting the work that was being done behind the ESDC project at Fort Hunter Liggett, which was very interesting project because it combined megawatt level storage and PV. Very impressive project. It was a lead on to another project that was done in concert with Xendee at the submarine base in Savannah, Georgia, which is really an ideal microgrid with nuclear. Findings directly inform the design philosophy. The findings of the work of the microgrid program inform the design philosophy for modern microgrid controls. These are the controls that you're seeing now in Xendee. The DOE vision was first resiliency, then efficiency, cost savings, and now we're at grid interactive grids at scale, where to whatever extent microgrids are being favored or disfavored by the Department of Energy. The program manager, the leader, the thought leader is Dan Ton, who many of you are probably familiar with. These systems were rule-based control. The transition from the government projects to commercial projects, commercial platforms and models came very rapidly and is meeting the challenge that we have today for a higher degree of interactivity, because it's not simply to island, it's how you interact and transition. I believe that the transition function was mentioned earlier as being the most difficult. And of course, reconnection and synchronization after islanding is the most challenging of all. But the DOE originated science now serves the AI data center microgrids at a gigawatt scale. And the modeling and control technologies have transitioned as well to model predictive control. These are the characteristics of rule-based versus model predictive control. I think that most of you are very familiar with rule-based control. Model predictive control is very, very, very important, especially because of the disruptions that can take place in large loads on the grid and the need to dispatch in very short time intervals in order to increase the value of the resources that are in the microgrid when it is not islanded or used actually to serve the loads of which it was designed for within its boundaries. Proactively managing demand charges is very important against AI forecasts. You have to be capable of doing that with model predictive control. And we can handle all the revenue aspects of it in optimization. So you can optimize actually outside of the grid. This has been done in Princeton, where they participate in the frequency regulation market for over 10 years, if you will. Now it's available as a package for modeling, design, and control systems that actually match that. This is very important to keep an eye on today. So I wanted to be sure to mention that this is part of this evolution. Okay, the standard. Now, you all probably come to the conclusion by now that I'm speaking from the point of view of IEEE Standard 2030.7. I consider the microgrid to be defined by the functions of its controller. The controller says what the microgrid is designed to do. If it's group control, it's designed to island and protect a particular load. If it's very sophisticated predictive control, it's balancing between the grid and the microgrid, making money and also being there for whatever needs that very complicated load profiles present, especially the interplay between, say, storage and solar within a microgrid that's out there. It's very large at the gigawatt level. So, and then the standard itself, it can be used as a framework for a microgrid energy management system very, very, very early on. And I think it's one of the very best references before you even enter the design stage, because the better design products, the design products that are not meant for a quick and easy calculation, these are the very early ones, or meant to promote particular technologies. You have to be technology agnostic and adaptive to the grid as well. I think that a framework provided by what's in 2030.7 is the most helpful. These are the specifications of the IEEE 2030.7. They're all things that you want to look at if you have a grid-connected microgrid, especially at scale that is going to be islanding. So obviously you're starting with the behavior into operating modes, and mostly dispatch and transition and reconnection are really the most important, because if you disconnect and you're not stable, well, you're going to not have anything. So then you're going into DER dispatch, load shedding, coordination with protection, which has become really, really, really important now. The microgrid controller can be constructed and designed and have the capability to handle different sorts of ride-through, for example. Then you have energy and power management. These are becoming very, very, very important as microgrids would become larger. And interoperability between all those that are interested in these very large microgrids. And grid services should be part of any microgrid that has excess capacity that's not being used because there's no emergency or no reason to be islanded. Okay, so here we go to the standard stack. You have certifications at the bottom. Very important to understand that. Device interconnection, that's your 1547, which is most common. 1547 originally was how you would connect, and anti-islanding was a big, big, big part of that. And then it kind of like had been used for connection and what we do if we do island. When we do island, it's a microgrid. So now we're going to do microgrid. It's not a system standard. The 2030.7 is a system level standard, integration of multiple resources with multiple functions that translate the grid requirements into the device commands. You will always want to use the ride-through, for example, of the devices, which are designed that way, but sometimes you might want to override them if you want to have wider ranges for voltage and frequency ride-through. And then at the very top level, you have grid reliability, you have the NERC standards, you have the grid operator protocols and FERC orders. These are very important. I mean, FERC 2222 is very important for aggregations and opportunities for the development of microgrids. As I said, 2030.7 is the organizing layer. Without it, everything else is disconnected and is not an operational system. System is very important to the conceptual approach to microgrids. There's a critical window that's open now because after 10 years, the standard has been renewed. And initially, as you could maybe surmise, it was sponsored, has to be sponsored by a IEEE committee. But originally it was like 10, 14 years ago, sponsored by the distribution subcommittee of the Transmission and Distribution Committee. It had to be renewed every 10 years. We started to do that this year. Well, really, we started in 25 because lead times with the Standards Association are very long. When it was sponsored this time, the entire T&D committee, because the connections of a large microgrid have to take place at higher and higher voltage levels. So the connection is now subtransmission, transmission, above, and the principles are the same. The functions are the same in the microgrid controller. Some of the interconnections and interoperability are different, but you can see that if you're a large microgrid or you're connected at a transmission level, your possibilities of participating in markets and to supply grid services to support the grid are far greater because you still have the resiliency aspect, but you don't want to have underutilized or not making the most money possible for the resources that you have. This is still going on now. We've had 9 meetings so far, and we're just starting a testing group. It will take account of many of the needs of the larger, more interactive microgrids. This is another chart that talks about the core functions. We're getting more into the nitty-gritty of the standard itself, and we're doing this within the context of data center controllers, because data centers are where the most advances need to be done. We used to have 3 levels. One were the asset level. That's the level that we talked about before, like 1547, individual item interconnection. The middle is the systems, which could be DERMS, energy management system, all different ways of looking at aggregations and the dispatch function. And then at the top, placing great emphasis on the interaction with the grid operator interfaces, if you will. But the center 2, they were broken out into 2 groups separately in order to function on the higher requirements for the grid interaction from a systems control point of view.
Jim, can you go back to that slide? Since I was interrupting everyone else, I need to interrupt you too.
Well, you can interrupt me on this slide just as well as the back one because I gotta figure out how to go backwards.
Just one back, please. Can you go back by one?
I'm going to try.
I might. Anyway, you don't have to go back. My question is, you make it sound like that the 2030.7 is specific for data centers, but it will apply, to my knowledge, to every microgrid, but there's a special focus on data centers, correct?
Any microgrid at all, period, doesn't make any difference. I developed the slides around data centers because that's what we're focusing on most now. That's where the differences and the updates are, but absolutely applicable to any large.
Okay.
The Illinois campus is bigger than most national labs, over 150 megawatts. That's one of them. It has SMR, has CHP, has solar, storage, demand response, connection to the grid, all of that. And that's been modeled already. And applies to all of that. All of the above, yes.
Thank you.
So you don't have to buy a data center to buy this control system, if you will. So this is another chart of looking at it from the point of view of using data centers. I guess we moved into data center too quickly there, Michael, but I'm on this AI track here. So this is another layout that shows the relationships to a distribution ADMS that you need to have interoperability with and a TSO, but also you're doing all the other functions of a microgrid, regardless of what the size of it is here. I just put the data center here. Okay, so now we're ready to talk about data centers again, because this is where the big play is today. For behind the meter power, 30% of new data centers being built this year have behind the meter power, and they're microgrids. So a little bit on this. Why is this so important? These will be the biggest microgrids out there. And actually, if you have behind the meter power and you have the controls to interact with the grid, you can expedite your grid interconnection. You move forward in the queue to interconnect because you're being allowed to connect and then manage later. You can't manage later without a system and a control system. And by the way, this applies to more data centers. It applies to crypto. Any other large microgrid would be. These would be valid for that as well. Okay. These are value streams. They parallel pretty much the ones that were earlier, but these are much, much more direct and direct to the needs of the data centers, which have very, very, very unique load profiles. We heard earlier about the difficulty of getting load profiles. Well, getting load profiles from a data center is like pulling shark's teeth. It's very, very, very difficult, but we've been successful in a couple of cases in the modeling and in the design area, and also with new technologies. But this is a chart that shows all of the things that would generate the value streams of the microgrid. The microgrid as a data center, and of course, it's to give you a longer period than the diesels would give you if you have to island, because you've got sources of power that are usually natural gas, could be geothermal or others. But you've got your own. You got a lot more than you got those two gigawatt level diesels there. So you can do something with it. The Idaho National Labs, which is the leading lab for SMR and nuclear power research, they have a data center. It's a digital twin, and it's used for the modeling and the calculations for all of the reactors that are being tested up there now, all the new ones that you're hearing about. And this data center that they have, this digital twin, the data was obtained under an NDA by Xendee, and they used the optimization science that came from the DOE, and they actually were able to model this and model it with a utility and model it with a DER and actually modeled it with an SMR included in the mix. Xendee is the only company that I know of that has modeled the characteristics of an SMR. And the results are there on the bottom. They were done in Idaho for the same load profiles and generation mix. And then, of course, in Virginia for Data Center Alley. this shows a different location. You can have different results, different optimization because of the tariffs and the sorts of load profiles that you might be seeing there. And it also shows that you can do these analyses in many different locations by going into the library of tariffs and rules for other locations. This is the data here is in seconds on a year's worth of data by seconds. So it's very good data. Here we go back as the grid. We're talking about a microgrid here. We're talking about large loads that have adopted microgrid concepts, which in order to operate need controls. And to need controls, in my opinion, you need to follow the standard. If you don't follow the standard, I don't think you're going to be able to communicate at the point of interconnection or operate at the point of interconnection. And this is a chart that puts the 2030.7 at the heart of the microgrid energy management system. So it is the framework, it is the center, it's basically the brains of any microgrid that has this level of power and this level of resources and this level of functionality. The three propositions for the microgrid data center nexus are, let's just pick 300. That's the average in Northern Virginia for a data center, even though some of them are quite old, or even 5 years old, some of them are more. So you want to be able to deal with grid disturbances, something that hadn't happened before. So the one reason to microgrid these facilities to bring your own power is because you want that to be controlled at the point of interconnection, and they're now being recognized on an equal level to IBRs and other generation sources, and they're being in the process of trying to get registered as computational load entities. Then 2030.7 is the organizing standard. And then, of course, we have the fact that the window's open to contribute, industry, government, whoever might be interested. Let's see here. This is the common thread. This is the common thread in the evolution. It's not one standard among many. It is the organizing intelligence that transforms isolated equipment into grid interactive systems at every scale across every era. And this puts me into the future, Michael, in which it's gotten dark.
Thank you, Jim. So we're a little bit over time, so I have only one question for you now, and then I have one final one for Melanie and Greg. But Jim, I think you didn't mention 2030.8 in this, which is fairly new, and maybe you want to open it also up to the audience if you want to join here, because 2030.7 is already pretty late, I think, right? I mean, they still can join, but yeah. I don't know the timeline.
Well, the companion standard for any standard is its testing standard, because it's only good as if you got a metric to test it against. We have an approved by Transmission and Distribution Committee to update the 2030.8, which is the testing for the functional requirements of the 2030.7. And our inaugural meeting is on this coming Monday, the 15th. And anyone who cares to join is more than welcome. We will be going through the 2030.7 somewhat in parallel with a couple month lag, and this is a very important new standard that we're starting, 2030.8. If you're interested in joining, you can email me or Michael knows how to find me. Be very happy for anyone who wants to join.
Okay, thank you, Jim. So one final question for Melanie and for Greg. And I have to ask this because I noticed from Greg's work in the past, and then Melanie brought it up. So why is it that we are building microgrids without having metering infrastructure in place? So I mean, how can these microgrids actually work? Or are you putting this metering infrastructure in place later on? I mean, how does this work?
Well, so one thing is once we build a microgrid, we generally now have metering infrastructure. So, I think at least for the bases, the Department of War and especially the Army, the funding isn't there for metering infrastructure, right? We had the meter data management system, MDMS, for a number of years. It wasn't perfect, but at least it was something. But in the last year, that's been defunded. And so we're all left a little bit empty-handed when it comes to metering data on the Army side. I wish uninteresting infrastructure things like metering could get enough attention to get the funding, to get the programs established, to have that data available ubiquitously. I don't know. I feel like why can't that happen is probably several levels above my pay grade.
Okay, no, but it sounds like you have to solve this problem then with the microgrid. I mean, you're not upgrading the sites which don't have a microgrid, but you have to upgrade it with the microgrid. I think that's
yes.
happening.
So in general, there is a I think it's what we call an engineering bulletin. They came out in the last year that basically said if you're doing electrical distribution system work, your project has to include the metering. We got to do the metering.
Yeah,
I think that was one that came out. So yeah, once we do install a microgrid, in general, that microgrid is going to provide a lot of metering, at least within its footprint.
Okay.
If not for the whole base.
Craig, I mean, knowing you, I think you have some opinion on that.
Well, the Army has spent a lot of money over the years just on metering. And many of the systems have all their buildings, or the newer buildings, or some of those that have been retrofitted have a building automation system where they actually can go in and look at the total consumption of the building. Most of these have the heating and air conditioning system, et cetera, all tied into it these days. But it's always a challenge. Things go down or weren't installed originally correctly. And we've looked at data time and time again that you say, well, that just can't be right because the numbers just don't make any sense. But it takes personnel and a lot of efforts to keep those systems up and running. So,
okay. Thank you. So I really want to conclude this. I want to thank everyone here, Melanie, Greg, and Jim, for participating in this session. It was a little bit of a long session. We had a little bit of a late start here, but everyone also on the attendee side who powered through this, thank you. And we have a 50-minute break, and those of you who are joining the last training session, it will start in 50 minutes, which is about financing. Thank you, everyone, and see you in the next session.
Thank you.
Thanks, everybody.